Well, we've learned that when a metal bonds with a nonmetal, it makes an ionic bond. And when two nonmetals bond with each other, they make a covalent bond. But what happens when a metal atom and another metal atom bond? Well, the result is something that we call metallic bonding. It's like covalent bonding. In fact, in a way, it really is covalent bonding. But it has a slight difference from what we see with nonmetals and nonmetals. In metallic bonding, the nuclei, the protons and neutrons in the nucleus, and the non-valence electrons, so all those electrons that are not in the highest energy level or the highest shell, they're in a lattice structure. In other words, what that means is they're in this sort of a grid, and each nucleus is centered in a certain position. And the valence electrons, the ones that are in the highest shell, well, they're free to float around within this grid of nuclei and non-valence electrons. And it's called like a sea. They're mobile, they're movable. Well, the attractions of the nuclei to these mobile electrons are what form the bonds. So it's an attraction of nuclei for electrons, and that's what covalent bonding really is. Except these electrons aren't bound to one particular position. They don't make one individual bond. They move around, they float around, and so it's sort of a free-form bonding situation. This is often called the electron sea model. And in this model, the electrons are like the sea, like waves sloshing around in the ocean, and the nuclei are like islands in that sea as they sit there in their lattice positions. This model accounts for the properties that we've learned that metals have. For example, metals conduct electricity well. So this is a picture of our lattice network of blue nuclei and the red mobile electron sea, the valence electrons. If I were to put a minus charge on one side and a plus charge on the other side, in other words, if let's say this is a piece of copper and I hook both ends up to opposite terminals of the battery, well, the electrons in here, all these negatively charged electrons, are going to have a tendency to move toward the positively charged end of this piece of wire. And because they're free to move, here's what happens. They flow towards that end. Now, if that positive charge and negative charge stay there, electrons are going to continue to flow. Electrons will come in from the negative end and disappear on the positive end. Metals also conduct heat really well. So what does heat mean? Well, if you put heat into an object, the temperature is going to go up because the particles will start to vibrate more rapidly. That's what a temperature increase really is. So if I start to heat up one end, the particles are going to begin to vibrate. But those moving electrons are going to bang into the electrons next to them and cause them to begin to vibrate as well. And that will just keep continuing all the way down the piece of metal. And so in the end, everything, even on the other end, starts moving at high speed. In other words, the temperature increases. Another property of metals is that they're shiny. They reflect all wavelengths of light. So imagine a wavelength of light is coming in here that's red. And that red wavelength hits an electron. The electron vibrates and goes up into higher energy levels because there's lots of energy levels possible with all these atoms close together. And that bounces out exactly the same color that came in. It can find exactly the jump that it needs to provide the same light output. Or green. Or purple. No matter what color comes in, there's exactly the energy jump that's needed to absorb it and then re-release exactly that color of light. And so most metals will reflect all colors of light, so we can use them for mirrors. Now there are some exceptions. Copper and gold come to mind right away. They don't reflect all the colors. They have this sort of a yellowish tint. And something in their electron structure explains that, but it's a little too complicated for right now. Another property of metals is that they're malleable and ductile. In other words, you can smush them and form them by banging into them with a hammer, and you can stretch them. And here's why this works. Because the mobile electron sea can sort of squish around to where it's needed to hold the nuclei together in their new positions as they get bent or stretched, it doesn't crack like this. As this bends, the electrons are just going to reflow and take new positions where they can hold the nuclei together in their new positions. That wouldn't work for nonmetals. If you had a piece of carbon, as you bent it, you would just be breaking all those covalent bonds and it would not reform. It would just be broken. So metallic bonding is a special case of covalent bonding, and it provides an explanation for the properties that we see present with metals.